11, page 220, problem 45. Take 2. Okay, so basically, if we take a look, I'm just going to write the whole shebang thing out. We have kinetic energy initial plus the potential energy due to gravity initial plus the potential energy stored in a spring initial plus any non-conservative work done is equal to the kinetic energy final plus the potential energy due to gravity final plus the potential energy stored in a spring final. Now, we know there aren't any springs in this problem, so that's going to go. Okay. They didn't mention anything about any air resistance, frictional force, anything like that. Non-conservative work goes like that. So basically what we're left with is, if I consider this point up here, the initial point, and this point right here, right before it hits the sphere as my final point, then the initial kinetic energy plus plus the initial gravitational potential energy equals the final kinetic energy plus.
Do we need the final potential energy to this at 0?
Correct.
Wait,
No.
what are you trying to find again?
The final velocity.
If we choose this to be h equals 0, then you're absolutely right. The final gravitational potential energy is 0. So what are we going to have then? 1/2 mvi squared plus mthi equals 1/2 mvf squared. So notice the masses are going to cancel out because there's a mass in every single term. So that mass goes, that mass goes, that mass goes. So I'm left with 1/2 the initial velocity squared. So that sucker wasn't starting from it. It starts with a velocity of 5 meters per second. So 5 meters per second squared plus the g right there is going to be 10 meters per second squared times h. They tell us the height off the ground is 0.300 meters, and that's going to equal 1/2 times the final velocity squared. And that's how fast it's going right before it hits the other sphere. And did you have to calculate that? 5.6 meters per second. So that's how fast this little small sphere is going as it swings down right before it hits the other sphere. You with me? Okay. So the next thing that goes on is an elastic collision. And anytime you have a collision, what's the first thing that should come to your mind? Momentum. Conservation of momentum. However much momentum there is to begin with, that's how much momentum there is right after the collision. Okay? So basically, I have that little sphere came down, and it's right about to hit the big sphere right there. Okay? And this is going to be like scene 1 right before the collision. And then, I don't know what the two of them, I'm sure they're going to smash into each other and bounce off of each other, and this is going to be right after the collision. This is after they bounce off of each other. Right. Bounce off of each other. Elastic, bounce off of each other. Okay, so I'm sure in the problem they told us the mass of each sphere.
Yes.
Right. So we know what M1 is. We know the mass of that little guy. What is that little M1? 1.5 kilograms. And we know what M2 is with M2. 4.6 kilograms. And we know how fast the little guy is coming in. How fast is that little guy coming in? What was it? 5.6? But the second one, what's its velocity? 0 meters per second because it starts from rest. Yes? And then after they collide, I don't know what they're going to do, but this one here is going to have some velocity. I'm going to call it v1f. And this one is going to have another velocity, v2f. And those are my two question marks. What's the final velocity of both spheres right after the collision? So first thing I do is I apply conservation of momentum, yes? So I know that the mass times velocity of the first little sphere plus the mass times the velocity of the big sphere, that's going to equal the mass times the velocity of the little sphere right after the collision plus the mass times the velocity of the big sphere right after the collision. Some people give them like little helpful subscripts. Other people find it confusing. I'm just going to leave it as it is. But you got to realize those m's are different and the v's are all different. So let's put in some values. Over here, the mass of that little guy is 1.5 kilograms, and we know its initial velocity is 5.6 meters per second. Yes? And then what about the momentum of the second guy? 0. And that's going to equal the mass of the first guy, 1.5 kilograms times the final velocity of the first guy, plus, 4.6 kilograms times the final velocity of the second guy. The problem is we can't solve that because we have two unknowns. But since it's an elastic collision, we could also apply conservation of kinetic energy. Yes? So basically, we know that 1/2 times the first mass times its velocity squared plus 1/2 times the second mass times its velocity squared is equal to 1/2 mass times velocity squared of the first guy after the collision plus 1/2 times mass times velocity squared of the second guy after the collision. And we put in the values again, and we get 1/2 times 1.5 kilograms times 5.6 meters per second squared plus 0 equals 1/2 times. No. Because this is right before it hits. This is right before it hits the other guy. And we figured out from part A that right before it hits the other guy, it's going 5.6 meters per second. So this is going to be 1.5 kilograms times v1f squared plus 1/2 4.6 kilograms times v2f squared. And now we have our second equation. And you can clean it up and like multiply all the numbers out on the left-hand side and, you know, drop the units and stuff and they look more mathematical. But the bottom line is you have two equations with two unknowns that you're going to have to solve simultaneously. It's very difficult though because the second equation has those squares in it. It can be done. It's just like grunt work. You would probably be asked to set these equations up, but you probably won't be asked to solve on the test. Now, as far as the homework, okay, there's two ways of going about actually solving these. Some people know how to put these two formulas in their graphing calculator and show where the graphs intersect, so they can get the v1f and the v2f by seeing the intersection of the two graphs. Okay, or the other thing you could do is in the textbook, if you did the reading through this, they actually solve this in symbols. And they tell you, like, direct formulas for calculating the final velocities of each one. So they actually did the whole thing in symbols. Why is what 0? Right here? Because you see the big sphere? It's at rest at the beginning. So before the collision, its momentum is 0 and its kinetic energy is 0. Okay, so now that you've figured out, let's say we figured out what those velocities are. Does anyone have those answers, by the way? Wait. Negative 2 point. And by the way, what does that mean? It's going to bounce off of it and start going back up that way. Negative, it's going back to the left. And what about p2 out? 2.73 meters per second. Okay, so now you know how fast that guy is going to go, yes? After you solve the two equations. So, for part C, thank you for reminding me that there's a part C. Basically, this guy is going up this way. This sphere is going back up that way. Well, what kind of energy does it have right after the collision? Kinetic energy, yes? But since they're both down on the ground, or what I'm calling the ground, since they're both down on the ground, what don't they have at the beginning? Potential energy. Now, basically what those spheres are going to do is they're going to go until they come to a stop. So they're going to be moving like right after collision really fast, a little bit slower, a little bit slower, a little bit slower, until finally they come to a stop. And at that point up here, what kind of energy are they going to have? Potential energy. So what's the bottom line? If you want to solve how high this is right here, yes, you could start with the big whopper equation, but the bottom line is, what's it going to simplify to? What are we going to solve? If we're just looking at this sphere right here. The kinetic energy that it has there at the bottom is going to equal to the gravitational potential energy that it has at the top. So the 1/2 mv squared at the bottom is going to equal the mgh at the top. And notice, even the masses cancel out here. And we know how fast it's going from the last part when we did the two equations with the two unknowns. So knowing how fast it's going right after the collision, we can solve for how high it swings up. So this velocity right here is from part B. And you have to do that for each sphere. If you're analyzing this guy right here, you would use this. But you also have to use the other velocity to figure out what happens with this sphere. Because it's going to do the same thing going up the other way. Yes, no? You follow me or not really?
Kind of.
See, you have the two spheres. They collided. You use conservation momentum and conservation kinetic energy so that right after the collision, you know how fast they're going when they separate. So you know their velocities right here and here. From part B, you know how fast this one's going this way, and you know how fast this one's going this way. Yes? But when they swing after the collision, because they're on strings,
They go up.
They start to rise up.
Okay.
You know, they start to rise up because like this is like up here. And as they start to swing up, they don't go as fast.
Okay.
So as they swing up, they slow down, and eventually come to a stop. And what's going on as they're rising up?
Yeah, it's converting.
It's converting to potential energy. So the kinetic energy that they have right after the collision turns into potential energy when they rise all the way to the top of the swing.
Okay, and that's when kinetic energy is zero.
And that's when kinetic energy is zero. Yes, no?